In this video, we're going to discuss Stokes Theorem. In multivariable calculus, a lot of the time we're discussing vector calculus as well. We're taking vector fields and we're looking at how they change and we're adding up little chunks, and that's why we need integration. We need things like volume integrals, surface integrals, and line integrals. So there's a lot more things you can do than just in single variable calculus. One very important theorem in vector calculus is Stokes Theorem. And there's a generalized form of Stokes Theorem, but we're not going to discuss the generalized form in this video. What we're going to discuss is the specific form for three-dimensional space, because that one has a lot of physics applications in electromagnetism and fluid mechanics and all of these nice little field theories. So we're looking at the physics applications of Stokes Theorem. Sometimes it's called the Curl Theorem or the Curl Integral Theorem. Why is that the case? Well, it's because we have curl inside of an integral. So we're relating integrals with curl. And that's actually one of the main uses for Stokes Theorem when we're looking at physical systems. So what this theorem is looking at is systems where there's something going around a closed curve, and anytime you have some kind of rotation. If you have rotation in vector calculus, you're probably going to invoke this operation, curl. Now this little upside down triangle is called Nabla, or the del operator. So Nabla, or the del operator, is it's being used with the cross product to take the curl of the vector field f. So this x over here, that's the cross product. So it's not the dot product, it's the cross product. This over here, that's a dot product, that's a dot product. This guy is a cross product. So what is Stokes' theorem, or the curl integral theorem? What is it saying in this form over here? What is this expression actually saying? Let's have a look at the left-hand side first. So the left-hand side is a surface integral of the curl of the vector field f. The right-hand side is a closed line integral. So it's a line integral over a closed curve. And that closed curve C is the boundary of the surface S. This little guy dl, L is a tiny little length segment along that curve. S is a tiny little chunk of a surface. That's why we're looking at ds over here and dl over here. With both of these cases, we're taking a dot product, but in this case, we're also taking a cross product. And this is curl. This is the curl operator. So del cross something, that's the curl of something. So del cross f, that's the curl of f. You might also see it written as curl, literally the word curl. But I prefer this notation because it's a little more condensed. So what is going on over here? We have two integrals. That's denoting a double integral because it's a two-dimensional surface. Here we just have one integral, and that's denoting it's a line integral. It's only one dimensional. Now you can have condensed notations where you don't write the double or the triple integral in the case of a volume integral, but in this notation, this is denoting a double integral over a surface, and this is a line integral over a curve. Now this curve is the boundary curve of S, right? S is some surface that lives in three-dimensional space, or it could be in two-dimensional space even, and this C is the boundary. So you can think of S as a domain, and the boundary to the domain is C. It's some closed curve. Now, what's really important is that this is a closed curve. That's why we have a little circle around this integral, because it's a closed curve, and we're taking the line integral around that closed curve. So C is the boundary of S. Now, let's draw a diagram to kind of visualize this. So we're going to draw a diagram, and first of all, let's draw the curve C. So C, let's say it's some kind of curve like this. So this is sitting in 3D space. That is C. And C, you can see it begins and ends at the same spot. So if you go around C, you have to also specify a direction. If you go around C, you're going to come back to where you started. So this over here, if we just had a line like this cannot be a closed curve. It doesn't enclose a surface, right? You can't use this and apply the curl integral theorem because it doesn't work. You have to have a closed curve. And we can also pick a surface. We can pick the surface here, right? This can be S. And equivalently, we can also pick a surface above here, like this. So imagine this is some kind of 3D It lives in 3D space, but it's a 2D surface. So this is like a bubble emerging out. So you can imagine this is kind of like you would dip a little plastic guide for a bubble into some soapy water, and then if you blow into that, you blow into the membrane, it would expand it out. So if you imagine this is like one of those little things that kids like to play with, you've got a membrane here, that's the bubble. So this acts as C, this is the contour, and what you can do is you can actually blow out all of this. And this is going to be, if I draw some lines to give more perspective, this is going to be a surface in 3D space. And it's going to share the contour C with the circle that's here. So this circle is going to have the same boundary surface as this guy. And you can pick another surface that's even longer. You can pick something like this, right? I'll draw these guys so you give more 3D perspective. This is going to have the same boundary surface. So all these guys have the exact same boundary surface, but these are different surface, the same boundary curve, the same boundary curve C. So all these surfaces share the same boundary curve C. We can call this one S1, we can call this smaller one S2, and we can call that one that sits in the plane, we can call that S3. So S1, S2, and S3 all share the same boundary, and that boundary is C. Now, these two examples, this guy, we can call this S1. That's the flat one that sits in the plane of the contour. Or we can call this guy S2. And both of these guys actually share the same C. This is the same boundary. So the two domains share the same boundary. So that's the point I'm trying to illustrate here. So if you were to look at all the circulation, all the little circulations in the vector field, what you could do is you could take the line integral, you could ride this contour around, and you would get this value here. So that's related to the circulation of the vector field. Equivalently, you could take the surface integral of the curl. So what does that actually mean? If we were to take some kind of, so this is some C, some general C, what we could do is we could follow this around. We could take a little chunk, so this is a tiny little increment, dl. I'm going to call that dl, right? So tiny little vector, dl. And then we could take the vector field, could be pointing in this way. That's f. We could take the dot product of those two values, and that would give us one of these guys. And then we would do that for all of this entire curve. And that would give us a line integral, right? We would have to parameterize this curve in order to actually compute the line integral. But if we were to take the dot product at every single point and then add it all up, take the sum, and let that sum tend toward, do the limit as this little dl goes to infinitely small, an infinitesimal chunk, then that would actually give us the line integral around there. But that's going to give us the circulation of this vector field around that curve. Equivalently, what we could do is we could take the curl at every little point over here. So imagine there's a little curl at every little point. So I'm drawing these little, it's like a snake eating its own tail, these little twisting guys. And what we could do is we could take every single point, add it up, take the integral over that surface, and that would be equivalent to this. So that's a visual intuition as to what Stokes' theorem is saying. It's saying take the curl at all these guys, add that up, do the surface integral. That's equivalent to doing the line integral along the curve that is the boundary for that surface. And you can have multiple different surfaces that are bounded by the same curve. That's what we saw over here. That's what we saw in this little bubble example, right? So in this little bubble example, we're not actually blowing the bubble, we're just extending the membrane. The moment you have a bubble, then you have a closed surface. And that's something that is more relevant for the divergence theorem. But here we're not talking about divergence, we're talking about curl. Right? So this over here, I'm trying to explain an intuitive visual approach to Stokes' theorem. Now, we'll come back to the intuition, but let's have a look at what curl actually is. What does it mean to take the curl? So there's a common way that we can actually take the curl. So I'll do a little computation of the curl in general. So if we want to take the curl of the vector, f, what we want to do is actually take the determinant of a 3x3 vector. Now this is just a trick, it's like a memory trick to work out what each of the components are going to be. Now, some people say that it's actually not just a little memory trick. It actually has physical significance, this determinant. But we won't go into the details of this physical significance of the determinant of this 3x3 matrix. We're just going to use it to compute the curl. So let's go ahead and do that. So if we compute the curl, first of all, we're going to have to set up this matrix. So we're going to need the 3 basis vectors for 3D space, which is I hat, j hat, and k hat. Then what we're going to do is we're going to take the partial derivatives, d dx, d dy, and d dz. So these are the partial derivatives. And then what we're going to do is we're going to take each of the components of f. We're going to have a look at fx, fy, and fz. And we want to take the determinant of this. So we're going to take the determinant of this 3x3 matrix. And if you're familiar with 3x3 matrices, you're going to know that what you can do when you take the determinant is you're going to turn this into a problem where you're taking determinants of 2x2 matrices. So let's go ahead and do that. So what we're going to do is we're going to take I hat, we're going to multiply it by the determinant of this guy, we're going to block off these guys, then we're going to take j hat, we're going to block off these guys, and then we're going to take k hat, we're going to block off these guys. So every time we pick I hat, j hat, or k hat, we're going to block off each of the rows and columns that correspond to that. Okay, let's do that. So first of all, I hat. What's the I hat? What's I hat going to be multiplied by? Or what's the x component of the curl? Well, I'll write some brackets. What we're going to need is we're going to need I hat. We're going to have to block out all of these guys. We're going to have to block out these guys. So there's not going to be any x's appearing in here. We're going to have this guy multiplying this guy, and this guy multiplying this guy, right? That's the determinant of a 2x2 matrix. You take these two guys, and then you subtract these two guys. So we'll take f of z, fz, which is the z component of the vector f, and we're going to take the partial derivative with respect to y, and then we're going to do the same thing with fy, but instead of the partial derivative with respect to y, we're going to have z. So let's go ahead and do that. So we're going to have d fz dy minus dfy dz. Now you can see in the x component, there's no x, and there's a z over here, there's a z over here, there's a y over here, there's a y over here. And we're subtracting these guys. The next thing we want to do is we want to find the j component. The j component, what is the j component? Well, we're going to have to take this column and this row, and we're going to ignore them, and we're going to take the determinant of this. But keep in mind, when you're taking the determinant of a 3x3 matrix, the signs alternate. So you have plus, minus, plus. But I've written a plus here, so what do I need to do? I need to change the order of the things we're subtracting. So let's go ahead and do that. So what we're going to need is, if it was positive, what we would do is we take this guy, and then subtract this guy and this guy. But because we need to flip the order, what we're going to do is we're going to take the partial derivative with respect to z first, and then we're going to do this guy. So we'll go d fx dz minus, now we're going to take, so we've taken this guy, now we're going to take this guy. So we're going to take the z component, and now we've got the z component, we're going to differentiate with respect to x. So again, the y component, which has j hat associated with it, doesn't have any y showing up in this partial derivative mess over here. There's no y's. In the same way, there's no x's over here. And the x's and the z's, they swap positions. Now, why did we swap these guys? It's because there has to be a minus sign. This is getting negated. So if we took a minus sign out here, what we'd have is this term would be first, right? You'd have this guy would come first, and then you'd subtract this guy, right? So z would come first, but because we're taking the negative, we have to flip these two guys, and z has to come second. Now let's do the final component, k hat. Now you can probably guess what's going to happen. We have k hat, we're going to block off this column and this row, and we're going to find the determinant of this. And it's going to be positive, right? It's not going to be negative. It's only negative for this guy. So we're going to have these guys come together, and these guys come together. So rub that out a bit. So this guy times this guy, and this guy times this guy. When we say times, we mean operating on, right? The derivative is kind of like an operator. It's a linear operator. So we'll take Fy, and we'll take the partial derivative of Fy with respect to x. And then what we're going to do is we're going to subtract the partial derivative of partial derivative with respect to y of fx. So that's what we're going to do. So we're going to take fx, and we'll take the partial derivative with respect to y. And let's see if we've done the right thing. This guy is associated with that, and this guy over here is associated with that guy. Right? And we take these guys first, and then we take those guys. So that's the procedure for taking a determinant of a 3x3 matrix. And it's actually used to find the curl. So this is a good way to remember the curl. Instead of remembering all of these components, it's much easier to remember this. Right? This you can immediately write down because it's very logical. It's natural. You've got x, y, z, x, y, z. All you have to do is compute the determinant. Let's make some observations about these guys. As we've said before, there's no x component here, there's no y component here, and there's no z component here. So in the x component, x doesn't appear. In the y component, y doesn't appear. And in the z component, z doesn't appear. In this case, z goes before y. In this case, x goes before z, but that's just because we flipped these guys. Why do we have to flip them? Because this is a negative sign. That's one of the rules of taking a determinant. You have to flip the signs for every time you do it for a 3x3 matrix. That's also the case for larger matrices that are n by n in general. So if we have this guy, y comes before x. So what have we learned over here? This is the curl. This is the full form of the curl. So if you know the components, the x, y, and z components of the vector f, then you can find the curl, right? And then what do you have to do? We have to take the curl, and you have to take its dot product with a normal vector that's normal to the surface. That's what this means. And then you have to add that up over the entire surface. That is equivalent to taking the line integral around here. So sometimes finding the left-hand side is going to be easier, and sometimes finding the right-hand side is going to be easier. It depends on the system. So if it's easier to find the line integral, and we're interested in finding the curl, then we'll find this first, and then we'll set that equal to the other side. But if it's really difficult to find the line integral, if it's really difficult to parameterize the curve, well then it's much easier to just take this side, find the curl, do the surface integral, and then find the line integral by just setting this guy equal. Right? So all you have to do is think about the system, think about what way is actually easier to find a solution to the problem. So these are all applications of Stokes' theorem. This is how you would actually compute the curl. The curl operation is probably the most important part of Stokes' theorem, because without curl, you wouldn't have all of these beautiful applications. But keep in mind, in the generalized form of Stokes' theorem, you don't actually need curl. This works in numbers of dimensions where curl is not even a meaningful thing, right? Curl is very meaningful in 3 dimensions and sometimes 2 dimensions as well, but it doesn't give us an intuitive feel for how things rotate if we're looking at higher than 3 dimensions. So what have we done? We've talked about the Stokes theorem, and we've talked about the curl integral theorem, as it's sometimes called. Now let's list some applications. Where would you actually use this? Well, you'd use this in Maxwell's equations for electromagnetism. In the Faraday-Maxwell equation and the Ampere-Maxwell equation, you can actually use this theorem to switch between integral and differential form. That's what this theorem is very useful for. You can also use this in fluid mechanics when you're describing systems where things are flowing around, like vortices. That's very useful as well. Anytime you have a system, maybe even birds or bees flying around, where you have some kind of curl, this is an excellent description. Right? So these types of theorems in vector calculus are very applicable to real-world systems. What I want you to take away from this video is how to compute curl, a good way to remember how to compute curl with this 3x3 determinant, a visual intuition as to how Stokes theorem can actually be used, and also the representation of Stokes theorem with these integrals, with this line integral and this surface integral. I want you to think about the balloon example. Think about the bubble example. I want you to think about the bubble example. Think about blowing bubbles. Don't talk about bubbles that are already being made. Think about the membrane as it bends. Think about bubbles that are being blown in the wind. Think about that membrane of soapy water as it moves around. The contour, C, that curve, is the same for all of those surfaces until the bubble actually forms. So think about that example, think about these diagrams, and try and get Stokes' theorem to sink in because it's very useful for vector calculus.